Alright guys, try this again. This is like the fourth, fifth, I don't know, something along those lines. Tried taking videos quite a few times, trying to get the method down here for how we're gonna run this. What I wanted to go through for our lab, I guess for our Friday lab, would be another stability problem, and maybe we'll look at a buoyancy problem. But I just figured I'd go through a stability problem that I know we haven't done yet. So these ones, this one here I'm going to do is 5.39. In this one, the problem states, I would suggest open up the book to page 113. You can kind of follow along. So 5.39, a cylindrical block of wood is 1 meter in diameter and 1 meter long and has a specific weight of 8 kilonewtons per meter cubed. Will it float in a stable manner in the water with its axis vertical? So it's sticking out of the water vertical. Let's get down our values. Free body diagram. First thing I usually draw, just thinking about the cylinder axis coming out of the water vertically. It does say it's going to be vertical, so it doesn't necessarily say how deep, if it's fully submerged. So we have this block in here. So the given values would be, well, it's 1 meter in diameter, it's 1 meter long, and we're given that it has a specific weight of our cylinder is equal to 8 kilonewtons per meters cubed. So we want to find will it float stably? I don't know. Will be stable. I don't know if that's necessarily a word. Stably. Alright, so what we want to do is, well, what does it mean to be stable, right? So if we flip over to page 103 here, for our procedure, this is the procedure we're going to be following for this. And basically, if it's stable, what that means is our y distance to our metacenter greater than y distance to our center of gravity of the cylinder itself. All right, so this is what we got. Did say water? I believe so. Water. So since we know it's water, specific weight of water is equal to, well, we're metric, so 9.81 kilonewtons per meter cubed. Alright, so we want to go through and solve this. So following this stability of floating bodies procedure, step 1, so determine the position of the floating body using the principles of buoyancy, right? So principles of buoyancy here is our static equilibrium case, right? So we have the weight, and we have our buoyancy force, FB. We are given our specific weight of the cylinder, and we're a specific weight of our water, so we can calculate these. So our weight and our buoyancy force, well, FB, if you remember right, is volume displaced times our specific weight of our fluid, which is water. Our weight is going to be equal to the volume of our cylinder times the specific weight of, in this case, our cylinder. W in there. Kind of confusing for water. Alright, so these are the two equations we need. Alright, equilibrium equation. Everything equals 0. We have buoyancy minus our weight. Well, we can calculate the volume of our cylinder. And we need to figure out how much displacement, is actually gonna, how deep in the water are we gonna be? So what is our value here? Alright, so in this case what we need to do is we need to figure out, alright, volumes, right? So volume of our cylinder is equal to, well, a circle times the length of the circle, cylinder, right? So we have pi d squared over 4, multiply that by our distance, 1 meter, well, d is our 1 meter as well, so 1 squared is 1, so we have pi divided by 4, and this will be in meters cubed. So that's one way to keep a very specific value. If we do this in our calc, we get so 3.14, or pi divided by 4 gives us 0.785. Alright, so we have that. We can plug that in. We know our specific weight of our cylinder, so we can get the weight of our full cylinder here. So plug in our value, 0.785 meters cubed, times our specific weight of our cylinder, 8 kilonewtons per meter cubed, and that gives us 0.628 meters, or no, sorry, this is meters canceled, so we're left with kilonewtons. Alright, so we have our weight. Now we need to figure out our buoyancy force. What basically keeps us up? So how far are we floating in the water? So our buoyancy force, using our equilibrium equation, is equal to our weight, and that's just to keep static equilibrium, right? So we've stated that our weight is equal to 6.628 kilonewtons. What we need to do now is plug in this FB equation into our buoyancy force down here, and then we're going to solve for how much volume we have to displace, and then we can figure out how deep in the water we got to be to displace our weight. So plug that in. FB is equal to V displacement times specific weight of water, all equal to 0.628 kilonewtons. We know our specific weight of our water, so we'll divide through by that. Our displacement is going to be equal to 0.628 kilonewtons divided by 9.81 kilonewtons per meter cubed. So our total displacement here is going to be 0.628, divide that by 9.81. We get displacement of 0.064. And that would be meters cubed. See right? 0.628. Yeah, guess so. Oh wait, hold on. Something up here. Something wasn't quite right up here. I think it's supposed to be 6. That's my problem. I multiplied by 0.8, not 8. Thought that looked small. So it's 6.28. 6.28 newtons. Kilonewtons. So I was going to say that volume did not look correct. Divide that by 9.81, and we get the 0.6404. I'll just leave it 0.64, and this is going to be in meters cubed. Right. So that's our total volume displaced, or not, well, it is our volume displaced that we end up having to displace to make that float. So now that we know our volume displaced, we can now calculate how deep in the water are we here. So in order to do that, I'm going to grab another sheet of paper. Try to keep these kind of in view. Alright, so how deep are we in the water? Well, looks like it's almost, right? Almost fully in the water, because we have 0.785 meters cubed for the total cylinder, 0.64 meters cubed for whatever's displaced. Alright, so how are we going to get that number? A lot of times they call this X in the book. I guess I'll kind of stick along those lines. They call this X, finding X, I guess. So what we want to do here is think of our volume displaced. It's going to be basically a very similar equation that we found for our volume of our total cylinder, because our diameter hasn't changed. The only difference here is instead of 1 meter to the top, we're only going to take the X, and we're going to solve for X here. So then we can plug in this 0.64 down here right into volume displaced, solve for diameter. Or no, sorry, not this. Solve for X. So let's plug in and solve for X. 0.64 meters cubed is equal to pi. Well, our diameter here was 1 meter squared. 1 meter squared is 1 millimeter squared, or 1 meter. 1 meter squared is 1 meter squared, basically. So multiply that by X. Solve for X. So everything gets basically ported over to the other side. Solve for X is equal to 0.64 meters cubed times our 4, divide by pi, and our 1 meter squared value here to where we know our units will cancel correctly. And that X distance ends up being 0.64 times 4, divide that by pi times 1. We get X is equal to 0.8148. So we could round that up to 0.815. That's the answer I get for this X distance, where we sit in the water, right? So we look at our procedure here. We want to determine the position of the floating body. So that's one of the first things we wanted to do. Next, we want to locate the center of buoyancy. Well, this one's a little bit easier now that we've got, you know, this x distance into the water here. So this center of buoyancy, really center a reference here from the bottom. We want to call this YCB. So the second one, locate center of buoyancy. And just draw this figure again. So we know we're right about there. Center of buoyancy, YCB. Well, we're going to the center, centroid of our displaced volume here, and that's what's going to be our center of buoyancy. So that's our y distance to center of buoyancy. And we want to solve for that. Well, YCB is just going to be half of our height, right? Centroid of a rectangular shape is half that centroid length. So in this case, since we know this x distance is 0.814, we can say YCB is equal to 0.8. I guess I'll round up to 815 right now. That gets divided by 2. And YCB will end up being 0.475, basically, if I did that correctly in my head. 84075. So I double check your answers. Alright, got that. YCB, good. Got our x distance. 3. Locate the center of gravity. Compute YCG measured from the same reference axis. So center of gravity. Center of gravity is going to be to the center of the full cylinder. Well, full cylinder is 1 meter high, right? So YCG is just our 1 meter divided by 2, or 0.5 meters. So 3 is done. Part 4 here. Determine the shape of the area at the fluid surface and compute the smallest moment of inertia for that shape. Well, if we cut this shape at the surface here, you know, what are we gonna see? Well, cutting it at the surface, I'm gonna see a circle, right? So we end up getting a circle here, and we have 1 meter in diameter, right? And we want to figure out what is our smallest moment of inertia. Well, basically we can look at this any which way and we're going to get the same moment of inertia since it's symmetric. So at this point we need to get that moment of inertia. So if you don't remember moment of inertia equation for our circles, come right back to the back of the book here. Moment of inertia around your axis on page 512. We have our circle, and that equation is pi times d4 divided by 64. So we have moment of inertia, IC, pi times d squared, d to the 4th divided by 64. Alright, so we want to solve for a moment of inertia. Well, 1 to the 4th power is 1 meter to the 4th, right? So we have pi times 1 meter to the 4th, all divided by 64. Just to make sure I don't make a mistake, punch that in my calculator. 3.14 divided by 64. Almost 0.05. So 0.05 0.049, round up to 1, and this is meters to the fourth. Alright, we got our moment of inertia now. Next step. Organize this up a little bit. Next step here, we want to compute the displaced volume. We've already done that. So basically 5 is done. So 5 volume displaced. Displaced we said was equal to 0.64 meters cubed. Alright, so now we want to compute MB, so metacenter from the buoyancy. It's called our MB value. And what this is showing us for, this is always good to show on paper or in a diagram of some sort that we have. So here's an example of what MB is. But we have our CB, right? So CB, center of buoyancy, and we have something that's called our metacenter, MC. We'll be looking for that in a minute. But what we want to basically figure out here is what our MB is. Metacenter from the center of buoyancy. And that's basically where everything kind of pivots back and forth, rocks. You could think of a boat rocking. It rocks along that metacenter. As you can see here. So as this boat rocks back and forth, its pivot point is basically right at that metacenter point. So to get MB, we do moment of inertia divided by our volume displaced. Over this, what do we get for? So we had moment of inertia. Here was 0.0491 meters to the fourth. Divide that all by our volume displaced. We said was our 0.64 meters cubed. So our metacenter to the center of buoyancy is, well, can't do that one in my head. 0.0491 divided by 0.64. So metacenter to or from buoyancy to metacenter, we get 0.0767. And that's just going to be meters. As you look, meters cubed, meters to the fourth, left with meters. So we have a distance from center of buoyancy to metacenter of 0.0767 meters. Alright, so what's next? Next, we look at step number, well, so step number 6, so step number 7. We want to compute YMC. We're given the equation here, that distance from the bottom, so this would be from the bottom up to our metacenter, would be center of buoyancy plus this distance between our buoyancy and our metacenter, so MB value. So that gives us, well, YCB. Go back to step 2. YCB we said was 0.4075 meters plus our MB value of 0.0767 meters. We get an MC value of 0.47, well actually 0.48 something, 0.75 plus 0.0767. So we get 0.4842, so I'm just going to leave it 0.484. meters from the bottom. And this is going all the way from the bottom here all the way to the top, YMC. Step 8. Basically, step 8 is what we were talking about initially. So, are we stable? Basically, is the next question. Are we stable? So we have if YMC is greater than or equal to YCG, then stable. In this case, our YMC 0.484 meters, and our YCG is equal to 0.5. So, well, it's pretty obvious that we don't get that, right? So, no. YCG is equal to 0.5. YMC we found to be 0.48. So because this is the case, we are not stable. Which isn't super surprising. Think about you think about a cylinder floating, bobbing up and down in the water. Most likely not the most stable thing. Right? Easy, most likely to flip and lay on its side. So that's an example of floating body of a cylinder. I'll be posting probably a couple questions here to do with primarily stability. I would like to couple problems that'll be similar to what you guys went through for your classwork this week. Example problems and the problem we just went through here. But please, if you happen to see something that didn't make sense or have a question on something, please let me know. We can go ahead and either set up a face-to-face chat or bounce emails back and forth. All right. Well, I'll be, I guess, talking at you guys here soon enough. All right. Stay safe.